why are we doing this? Why is this at all useful? Well, what we've done is we've put together a really simple mathematical model of population growth. And it does capture something that is true about all populations. This is what I mentioned with the aphids, is that all populations have the ability, if they're not limited by food or predators or something else, to grow exponentially, and it's extremely powerful. This is going to happen faster when R is very high. What you'll see in a population where it has a very high value of R is it's going to very rapidly go through a population explosion. But even populations that grow very slowly will start growing faster and faster and faster as time goes on until they're exploding as well. What can we do with a mathematical model like this? Why would we bother building one? The nice thing is that once we've got some kind of statement about reality in the language of mathematics, we can manipulate that math to learn things about that reality. For example, sometimes you can look at this mathematical model and see how it changes to grasp some basic truths about a growing population. So, for example, you might not have realized that a population that's growing without any limitations, without any limitations due to food or predators, for example, is going to grow faster the bigger it is. But you can look at this equation and see that. Okay, another even more useful thing you can do, and usually you have to plug in the actual numbers to do this, but you can use a model to make predictions. And that's really important in a lot of the environmental sciences. So, for example, if you're worried about whether or not a population is going to go extinct, some species might go extinct, for example, it's better to look at a mathematical model and get an estimate of whether or not it's going to go extinct, rather than wait and see. Thirdly, finally, when you compare a model to reality, if they don't match, that tells you there might be something important that's missing in your model, and it can point you toward what you need to be thinking about. Okay, let's take a look at this. We've already seen a little bit of that first point, that you can look at a model and say, oh, okay, population growth is faster when the population is large. I see how I can manipulate the model to see something about reality. But let's go ahead and take a look at how we can use a model to make predictions. We're going to look at an actual historical example, which took place in early 1800s near Australia. In fact, it actually happened down here on the island of Tasmania. Between 1810 and 1820, sheep were introduced to Tasmania for the first time. There are about 100 sheep on the island in 1820. So we started out with something like 25 in 1810. By 1820, you had 100. And you can calculate a population growth rate based on these numbers. If you do the math, you find that, okay, this population is growing at an amount of about 16%. And then you can ask yourself, if this population is growing at a rate of 16%, how many sheep should we see in 1830? This is useful if, for example, you're trying to figure out what the price of mutton is going to be in Tasmania, or if you're worried about how big the sheep population is going to get, which is often what environmental scientists are thinking about. Well, if you do the math, it turns out that our model predicts that there will be about 500 sheep by 1830 if the exponential growth model contains everything you really need to know about this sheep population. According to the historical record, there were about 500 sheep in Tasmania as of 1830. So wow, it looks like this really simple mathematical model that we've got actually is predicting the future with some accuracy. Okay? However, if you keep going out to 1840, 1850, and so on, something interesting starts happening. If the population of sheep on Tasmania continued growing at a rate of 16%, then by 1840 you'd expect there to be nearly 2,500 sheep. In fact, there are only about 1,000, and it gets worse in 1850. The actual historical numbers of sheep in 1850 were about 2,000, but our model predicts a result that is basically insane. Over 12,000 sheep are expected if this population were to continue growing at a rate of 16%. Okay, and this brings us to our third advantage of a mathematical model. We've got a mismatch between what our model is telling us and what reality is showing us. And that tells us that this exponential model of population growth is leaving something out. And this shouldn't surprise us. You don't have to think too hard about ecological realities to recognize that, while a sheep population can grow at a rate of 16% under ideal conditions, conditions won't stay ideal if the population keeps growing. Inevitably, as a population grows, the world gets a little less perfect. After a while, there isn't food everywhere. Sheep have to go long distances in order to find food to eat or maybe water to drink. Maybe diseases start spreading. Maybe there are territorial fights because the sheep don't have enough space. Whatever, there are all sorts of reasons why life might become harder for an individual sheep. And that's going to end up having an impact on the sheep's ability to replace themselves. As there get to be more and more individuals in an area, it becomes harder and harder for each individual to have enough offspring to replace themselves. And the precise reasons why don't actually matter. This is going to happen to every population, anywhere, under any circumstances. Eventually, they're going to run out of something. And as they do so, population growth is going to get slower and slower and slower until finally, each individual in the population, on average, is only barely going to be able to replace itself. So for example, each pair of tuna or each pair of sheep, even though they love each other very much, they're only going to be able to get 2 offspring to maturity, and the population is not going to be growing or shrinking anymore. As human beings, we tend to think of other human beings as being our friends, our allies. But for most species, they really don't think of one another this way, because in most species, individuals don't cooperate with one another. They are one another's worst competitors, in fact. The reason is that another individual of the same species has the same niche that you do. It has the same needs. It's going to eat the food that you need to eat. It's going to use the nesting site that you need to use. Everything that you need, other individuals of the same species are going to try to take away from you. Competition within a species for resources is extremely powerful. And eventually, competition for resources is going to completely stop population growth of any population. This is why there is not a pile of aphids that is larger than the planet Earth, because as the number of aphids grows, eventually they run out of something. And the population, it gets harder and harder for the population to grow until finally it doesn't grow anymore. It reaches a more or less stable size and it stays there. Can we build a model that does a better job of predicting what's going to happen than the exponential equation does? Well, here's what ecologists have come up with. This looks ugly, but don't worry. Most of it is what you've already seen before. Here's the rate at which the population is growing. Here's the rate of increase, basically what each pair of sheep or tuna is able to do in terms of replacing itself under ideal conditions. Here's the population size. Put together, that's just the exponential equation, which you've already seen. All that we're going to add to that is this term in here, k minus n over k. What does that mean? Well, again, let's take our gut approach to this and tinker with it to see what it means. Ecologists define this term as the fraction of resources that are available for population growth. In other words, how many resources are there in the environment that aren't used up by individuals just replacing themselves? How much is surplus that can be used to grow the population? Intuitively, you can look at this and say, well, what does this look like when n is very, very small? When you've got a really small population? Let's say that k is 1,000,000 and n is 100. Well then, I mean, this is practically zero compared to this. And you might as well just toss n out. Then what you're left with is k over k, or 1. This whole term then just falls out of the equation. And you've got the exponential equation all over again. The rate of population growth is equal to r times n. What does that mean in kind of everyday English? Well, it means when a population is very small, it's able to grow more or less exponentially, just like the sheep did when they were first introduced to Tasmania. And this is true, it turns out, in all sorts of cases. Often when a population or an organism is first introduced to a new area, it'll go through a population explosion. This has happened many, many, many times throughout history when human beings have introduced a new organism to a place where it has lots of new resources and very little competition. Let's take another look at this, though. Okay, what happens when n and k are equal? What happens when they're the same size? Well, in that case, k minus n is basically 0. And if this term is 0, then it doesn't matter how big r is. It doesn't matter how big n is. Population growth is going to stop. So what we're seeing here is that when n is very small, a population grows essentially exponentially. It goes faster and faster. It grows faster and faster the bigger it gets. But as it starts approaching some size, it slows down and slows down and slows down until when n is equal to this number k, it stops growing entirely. This is called the logistic growth equation. And here's how it behaves. When a population's small, you get this accelerating growth, exponential growth, but then the population starts running out of resources. And it's as the population approaches the carrying capacity of the environment, population growth slows way down. What is the carrying capacity? Well, the carrying capacity is essentially, the maximum number of sheep that the island of Tasmania can support. It's the number beyond which the sheep run out of resources to the point where they can't replace themselves anymore. What generally happens in populations in the wild is that they grow rapidly when they're small, and then as the population runs out of resources, the population size is going to stabilize at something that we call the carrying capacity. This is what it actually looks like in Tasmania back in the 1800s on into the 1900s. The population of sheep leveled off around 1,500 individuals, and though it wobbles around quite a bit, you can see that it kind of is stable around this carrying capacity. So the logistic equation introduces a new factor. When we looked at the exponential equation and we compared its predictions to the actual number of sheep in Tasmania, we realized, there's something missing here. This equation works fine when a population is small, but as the population grows, there's something else we need to put in that equation. There's something else we need to take into account. And that something is competition among individuals for resources. Okay, so what the logistic equation over here takes into account is it takes into account the ability of a population to grow exponentially when it's not limited by resources, but its tendency to level off at a carrying capacity when it is. So these are the two most famous equations for population growth. You've got the exponential growth equation and you've got the logistic growth equation. These models, particularly the logistic model, has been used, or more sophisticated versions of it have been used to do things like manage fisheries or predict what's going to happen to an endangered species and so forth. And they're extremely powerful tools for doing this. But I want you to keep in mind one thing that's very important. All mathematical models oversimplify reality. Okay? This was abundantly proven to the human species when a tremendous number of the fisheries that were being managed across the globe began to collapse. Fisheries collapses are a very serious problem today. It's something like a third of all of the fisheries worldwide have completely collapsed. They've collapsed to the point where they can't really be fished anymore. And if this continues, there really aren't going to be very many fish in the sea by about 2050. Why did this happen? Well, one of the reasons that this happened back in the 70s before more sophisticated models were developed is that you take a look at the carrying or the logistic equation, and it predicts there's a carrying capacity here, and it predicts that the maximum growth rate of the population is right here, where the population size is about half the carrying capacity. This is the size you want a population to be at if you're managing a population for maximum sustainable harvesting. Because what can happen when a population is growing very rapidly is it starts out at this size and it shoots up to here. And then you can take this many fish. And it goes right back down to this size and then shoots up again the next year. And you take that many fish and it shoots up again. And you take that many fish and it shoots up again and so on. But you can take that many fish, and it can be a fair number of fish, every year without the fishery collapsing. And that sounds great. And so that's the approach that a lot of managers were using for fisheries. There's just one problem, is that the logistic equation is only an approximation of how a real population behaves. In reality, the carrying capacity doesn't stay the same from year to year. Some years it drops way down because, let's say, there's a bust in the food population for whatever reason. Let's say there's a disease among whatever food the tuna are eating, or there's some weather extreme that kills off a lot of individuals in the population, and all of a sudden the carrying capacity you're dealing with is lower than you thought it was. Well, what happens then is the population, instead of growing this much, it only grows, let's say, this much. But you don't know that. And so you take the same amount that you've been taking every year. But instead of knocking the population back down to here, what you're accidentally doing is you're knocking it back down to there. And this population, a population of this size, actually does not grow as fast as a population that's up here. And so when this population tries to grow, it only grows up to here. And because you don't realize that this is happening, you take the same number of fish that you've been taking, and the number of fish in the population drops down even further. And so population growth rate slows, you take the same amount, it drops down further, and population growth rate slows even more. And what's happening is you're getting into what's called a death spiral. The population gets smaller, and so it grows more slowly, and so it gets smaller still, and so it grows even more slowly still, until finally you're down here in the area that's called a fishery collapse. This is what happens if you naively use an oversimplified model without thinking about the assumption that it's making and whether or not those assumptions might be false. So one thing you have to be very careful about when you're looking at the results or the predictions of any kind of mathematical model, in any setting, anywhere, not just biology. But you have to ask yourself, are the assumptions here true? Are they going to hold? And what happens if they don't?